So welcome everyone to my Viva presentation entitled Development and Characterization of a Zero Moment Half Metal. So I would first like to acknowledge people who I worked with during my PhD, in particular my supervisors, Professor Michael Coey and Dr. Karsten Rode, the past and the present members of the Magnetism and Spintronics group at Trinity College, and also our former group member Davide Beto, who was our local contact at the European Synchrotron Research Facility. Below are the funding agencies which made my PhD work possible. My talk will begin with motivation and background in the study of zero-moment half-metals found in the Heusler alloy material class. Manganese 2 ruthenium gallium will be introduced, and I will explain what is so special about it. Then we will move on to a summary of my PhD work. The main results of the magnetic annealing and magneto-optical Kerr effect studies of MRG will be summarized, and the remainder of the talk will focus on composition variation in MRG and XMCD measurements. I will finish with a conclusion and an outlook. The big data revolution has witnessed an exponential increase in magnetic recording density following Moore's law. However, data rate has not enjoyed the same increase. The chip-to-chip communication between the CPU and memory is the bottleneck to the powerful computing facilities due to lack of a practical chip-based solution to produce and detect electromagnetic waves in the spectral range between 100 gigahertz and 10 terahertz, known as the terahertz gap. So in the diagram I'm showing on the slide, I am basically outlining the terahertz gap. So spintronics has the potential to advance data transfer speeds into the terahertz gap using zero-moment half-metals. So this material is ideal for this purpose because it has zero or small net moment, no stray fields, high spin polarization of Fermi level, low Gilbert damping, and also a high ferromagnetic resonance frequency. And we can distinguish two modes, the ferromagnetic one, which is proportional to the anisotropy field, which scales as 1 over saturation magnetization. So of course, as the net moment goes to zero, the anisotropy field goes to almost infinity. And then we have the antiferromagnetic mode, which is proportional to the square root of the product of the exchange field with the anisotropy field, where the exchange field is proportional to the inter-sublattice exchange coupling. So as I mentioned, the first member of the zero-moment half-metals was manganese 2 ruthenium gallium. And here I am showing an illustration of a chip-based heterodyne terahertz transceiver based on a zero-moment half-metal material in a spin-torque oscillator. In such devices, the stray field would be negligible, hence crosstalk between magnetic elements is minimized. The high ferromagnetic resonance frequency means the device can operate in the terahertz frequency range, and high spin polarization ensures a high TMR ratio. So there are three main characteristics of zero-moment half-metal thin films with perpendicular magnetic anisotropy. The first one is half-metallicity, which gives you an ideal 100% spin polarization at Fermi level. Secondly, we have the existence of a compensation point at a particular temperature. And last but not least, we see that the coercivity of the material tends to infinity as the net moment tends to zero, closer and closer to compensation. So as I mentioned, the first zero-moment half-metal that was discovered is a member of the Heusler alloy family. So I want to talk a little bit about Heusler alloys. So it is a rich family of over 1,000 compounds, which exhibit many properties relevant to spintronics. And this includes half-metallicity and ferrimagnetism. So this material class is a promising place to start in the search for zero-moment half-metals. And this is because the Heusler stoichiometric half-metals obey what is known the Slater-Pauling rules. And the Slater-Pauling rules relate the number of valence electrons of the compound to the ground state magnetization, which is an integer number. So the idea is to take a Heusler half-metal and find the right composition of valence electrons in order to achieve a net ground state magnetization equal to zero. So here I am showing an example for cobalt-based compounds and how they follow the Slater-Pauling law. So we can see that the ground state magnetization, which is given in, this is in magnetic moment per atom, in mu b on the y-axis, is related to the valence electron count. So for full Heusner materials, which have the form x to yz, the magnetization m is equal to 24 minus z, where z is the sum of the valence electrons of the constituent atoms. For half Heusner materials, which have the formula x, y, z, we have m is equal to 18 minus z. So now to give you an idea of how we can do this calculation to predict a zero-moment half metal, we take first a half Heusner material, which is manganese 2 gallium. And when we calculate m, we find that we get +1 mu b. Then for a full Heusner, which is manganese 2 ruthenium 1 gallium, we obtain -1 mu b. So by tuning the ruthenium content, we can achieve a composition which can lead us to an m equal to 0. So manganese 2 ruthenium gallium thin films are grown by DC magnetron sputtering on single crystal MgO 100 substrates. The films crystallize in the inverted Heusner structure. Biaxial substrate strain induces a tetragonal distortion of about 1%, and hence the net moment exhibits perpendicular magnetic anisotropy. It should be noted that MRG is not an antiferromagnet because there are two inequivalent antiferromagnetically coupled manganese sublattices, with manganese occupying the 4A and 4C Wyckoff positions, as shown in the ball and stick diagram. Therefore, the two sublattices will contribute differently to the density of states, allowing for a spin gap, and the sublattice moments will have different temperature dependence, which will allow for compensation to exist. The spin polarization measured by PCAR is about 60%. This is far from the ideal 100%, but even in the cobalt-based half metals that I have shown you in the previous slide, the spin polarization is not too far from 60%. I think it could be up to 70 or 80%. So the TMR was found to be up to 40% measured between 10 Kelvin and 300 Kelvin for MRG integrated into MgO-based perpendicular magnetic tunnel junctions. Time-resolved MOPE measurements so far demonstrated a maximum zero applied field resonance frequency of about 160 gigahertz, and the intrinsic Gilbert damping constant alpha was found to be 0.02. So this is fairly low, as we would have expected. So we have also observed thermally driven single pulse optical toggle switching, which is shown in the picture on the bottom right, where I'm showing you the number of pulses which were executed at the same spot. And we can see how the magnetization basically alternates from up to down. Now for some magnetotransport, which I'm showing in the bottom left. Those are measurements of MRG blanket films taken at various temperatures, where I demonstrate that indeed the anisotropy field and also coercivity is inversely proportional to the net moment. So for this, in this example, the compensation is close to 300 K, where we measure coercivity in excess of 12 Tesla. And below, we see a coercivity of about 1 Tesla, and above, we also here see a coercivity of about 1 Tesla. So it sort of slopes off. And another thing that should be noted is that after we cross compensation, the anomalous Hall effect coefficient changes sign, which is another indication of compensation. And what we find is that the compensation temperature increases with increasing ruthenium content in MRG thin films. So prior to its discovery in 2014, there were many zero moment half metal candidates that were proposed by density functional theory calculations, but none of them proved successful. And this is quite interesting, and I wanted to take a few minutes to discuss what is special about MRG. So to do that, I'm going to break up MRG into its constituent elements and discuss how each element influences the material. So first, starting with manganese, it is like a Goldilocks element. So here we have an illustration of Goldilocks drinking the porridge that is not too hot and not too cold. And this refers to the SD coupling of manganese, which allows for the spin gap in the density of states and therefore high spin polarization. And it also is not too strong or too weak for antiferromagnetic coupling of the two sublattices. Then if we look at the periodic table, if we were to, for example, replace manganese with chromium, it would mean that the SD coupling is weak and the proposed spin polarization would then be low. And also looking at elements to the right of manganese, so for example, iron, this would lead to the SD coupling being stronger, which would then give rise to ferromagnetic ordering, and we wouldn't have compensation. And one of the conclusions here is that it is possible that most, if not all, zero moment half metals will contain manganese. And this is an important conclusion or, well, thought, because then we have a challenge that's associated with manganese based materials being integrated into spintronic devices, and that is the problem of manganese diffusion, because it's an important step in the fabrication of, for example, magnetic tunnel junctions. So addressing the problem of manganese diffusion will be later discussed in my presentation. Then we have ruthenium, and ruthenium has two important roles for MRG. It improves the wetting of the thin film onto the MgO, and it also adds 2 electrons per ruthenium to the density of states, which helps position the Fermi level in the spin gap. Hence, we can have high spin polarization. Then following the Slater-Pauling rule and the number of valence electrons, it would be a natural choice to try to replace ruthenium with iron to see if we get a new zero moment half metal. And this work has been done before in the group. And unfortunately, manganese 2 iron gallium is not a zero moment half metal. It is a ferromagnet with a tetragonal DO22 crystal structure on MgO001. And on the right hand side, I'm showing some magnetization curves. So it's magnetization versus temperature, showing the typical ferromagnetic behavior. Then another choice would be put in another manganese. However, that is also not a zero moment half metal. It's a ferrimagnet that crystallizes in the tetragonal DO22 structure on various different substrates that I've listed on my slide. Last but not least is gallium, which also plays a very important role in MRG. And the work that was done in the DFT calculations shows that manganese 4A, gallium 4B anti-site defects, those are defects where the two species of atoms basically replace each other in their positions or exchange positions. So those anti-site defects help in the opening of the spin gap at the density of states. They explain the non-volume conserving tetragonal elongation of the cubic unit cell, and they also predict the correct magnitude for the net magnetic moment in the ground state. And of course, again, considering our Slater-Pauling rule, it would be a natural choice to try to replace gallium with aluminium. And this is indeed a zero moment half metal. This is my own work that I have done showing here anomalous Hall effect loops for various ruthenium contents. And we see this characteristic change of sign of the anomalous Hall effect coefficient as we cross compensation. Now, but you can see there's no massive increase in coercivity, but this is because the films are crystallized basically in a cubic structure. There's very little tetragonal distortion. So the films are fully in plane. There's no perpendicular isotropy. However, they do show high spin polarization. And just to mention, there were other zero moment half metals discovered. One was prepared in bulk, that's manganese 1.5, vanadium 0.5, iron, aluminium, and also manganese 3 aluminium thin films grown on gallium arsenide. So once again, we see manganese in both of these compounds. So now moving on to a research summary of my PhD work, which consists of 4 parts. Firstly, the results of magnetic annealing to investigate the manganese diffusion, and also magnetic domain structure and reversal in MRG will be summarized briefly. Then I will move on to discuss the composition variation and also XMCD in more detail. So this will be the main focus of the talk. So first, looking at the effect of magnetic annealing. So one part was just annealing blanket films up to temperatures of 400 degrees C. And what we find is that annealing up to 350 does not strongly affect the films, and this is compatible with CMOS backend processing. Then we've also prepared GMR spin valve type heterostructures where I'm showing a stack diagram on the right-hand side, and they were also annealed in a magnetic field at 350 degrees C. The spacers chosen for this study were basically selected based on their performance as diffusion barriers and also their lattice parameter in order to match that of MRG. And they were deposited at 2 different thicknesses. What we find overall is that titanium, hafnium, and molybdenum are effective at preventing diffusion. However, each of these spacers is associated with a disadvantage. Those disadvantages include alloying at interfaces with cobalt, reduction of perpendicular magnetic anisotropy of the cobalt-platinum multilayer, and also diffusion of spacer material into MRG, which can affect the properties of MRG, such as compensation temperature or even spin polarization. So in conclusion, any one spacer was found to have a positive impact, but also it could have a negative impact at the same time on other properties. However, hafnium and molybdenum presented a compromise and are the best candidates for spacers reducing diffusion. Next, I will give a brief account of the study of magnetic domain structure and reversal. So, as I said before, MRG has negligible or zero stray field. So how could you possibly look at the domain structure? So there are some techniques that are used, for example, for antiferromagnets that could be like neutron diffraction. But we use the fact that the Kerr rotation is proportional to the manganese 4C sublattice magnetization, because only the electrons on the manganese 4C sublattice contribute to the transport. And therefore, it is possible to probe magnetic domains by using a Kerr microscope. And so I'm going to show you some domain images. So we found 2 different magnetization reversal processes. The first one is the domain wall motion dominated. And here we can see domains that have a dendritic type of structure. The second type of reversal process was nucleation dominated. And with the process can be set in the sample by depositing it at different temperatures, but also by varying the composition. So we can control which kind of reversal process occurs. So now moving on to the varying compositions study. So first, I want to give you the aim. So what we wanted to do here is identify compositions which exhibit the best combinations of properties for a specific application. So for example, for thermal all-optical toggle switching, we need the MRG to have T-comp above room temperature. So in order to be able to tune, we wanted to vary both manganese and ruthenium. And so first, I want to show you this bar chart, this histogram of the densities. So it is very important that when we vary manganese and ruthenium contents, we wanted to see if we have vacancies or if we have full occupancy. And in order to do that, I deduced the density of the films using XRR. So I was able to fit the XRR pattern and then derive the density. And that's given by the orange bars. Then using nominal compositions of densities, I calculated it for full occupancy, which is given by the blue bars, and also allowing for vacancies or interstitials. And those are given by these crossed yellow bars on top of the blue bars. So then when we compare the two sets of data, we see that we have an indication that in all the film compositions, we have full occupancy of the sites. And this suggests that there will be chemical disorder which can influence the exchange constant. So this is something to keep in mind, and I will discuss this in this part. Then what is also important, because we have two different manganese sites, we need to determine which manganese sites are being influenced by the manganese variation. I will discuss my mean field theory model fits of the net magnetizations where I was able to extract the exchange constants. And I will then discuss my results from SQUID magnetometry, as well as anomalous Hall effect and PCAR. So first, looking at the model, here I have the temperature dependence of the two sublattices. So we look at the solid lines first. So this is the 4C sublattice in blue and the 4A sublattice in red. And so if we imagine the manganese 4A site is being manipulated, if I remove manganese from that lattice, then the magnetization will decrease. And that leads to an increase in compensation temperature. So you can see that there. Whereas if I was to increase the magnetization, that's like adding manganese onto the sublattice, that would lead to a decrease in compensation temperature. If we do the same exercise for the 4C sublattice, keeping manganese 4A constant, decreasing the moment on 4C would decrease T-comp, whereas increasing would increase T-comp. So now, because we have an idea how T-comp will vary as manganese is varied, we can look at the data and determine which site is being manipulated. So here I am showing the variation of T-comp for 3 ruthenium series with x equals 0.5, 0.7, and 0.9, and I'm varying manganese shown on the x-axis. As you can see, as manganese increases in every series, the T-comp also increases. And as I've mentioned at the beginning of the presentation, increasing ruthenium content also gives an overall increase of the T-comp. So this is all consistent, and now we know we're mainly affecting the 4C sublattice. So now looking at the mean field data, the magnetization curves at 0 applied field were fitted using the Weiss mean field theory model, described by a system of linear equations, which is shown in the blue box, and the curves are shown here on the left-hand side. In the middle, I show the calculated 4A and 4C magnetizations, and the triangles represent temperature-dependent MOC data that was collected from the MOC microscope. And as I mentioned before, the Kerr effect is proportional to the manganese 4C. And so we can see we have a good agreement between the model and the data, which validates our calculations. So from these fittings, I can extract these Weiss constants and convert them into Heisenberg exchange energies. And they are summarized in the table. What we find is that JAA and JCC, so the intra-sublattice couplings, are positive, and meaning they are ferromagnetic as we expected. JAC, the inter-sublattice coupling, is negative, indicating antiferromagnetic coupling. The hierarchy of the exchange constants is that the magnitude of JAA is larger than JAC, which is larger than JCC. So the exchange parameters depend on manganese-manganese distances in the unit cell. And in the next slide, the manganese-manganese distances will be shown for an ideal MRG case, as well as for MRG with a different stoichiometry with 2 types of disorder that can occur. So here I'm showing the unit cell again. Below the unit cell, I'm giving all of the distances between the different manganese atoms. And on the very bottom, I'm showing a scale of distances where between 280 and 250 picometers distance, we can get antiferromagnetic coupling, and anything above 290 picometers leads to ferromagnetic coupling. So this corresponds to what we find from the distance analysis. So the first type of chemical disorder that I will introduce is manganese atoms occupying 4D sites. So to do that effectively, I'm going to zoom into the 4C sublattice part of the unit cell, which I'm showing here. And this is for the ideal or for fully occupied composition, manganese 2, ruthenium 1, gallium. So now introducing some disorder, I have replaced the ruthenium atom with a manganese atom. So this would lead to a composition of manganese 2.25, ruthenium 0.75. So as you can see, the distance then between the neighboring manganese atoms is 298 picometers, which would lead to ferromagnetic coupling. And so this is our conclusion. Then the second type of disorder that I want to include was the one I've already mentioned at the beginning, which is the manganese 4A, gallium 4B anti-site defect. And so I'm going to keep the disorder I've introduced before and include the replacement of a gallium atom with a manganese atom in the middle. And as you can see, the distances then between the neighboring 4C and 4D manganeses would be 257 picometers, leading to antiferromagnetic coupling. What does that mean? Well, anti-site defects could lead to competing exchange, which could lead to a non-collinearity of the sublattice moments. And this is an important consequence. And this non-collinearity could manifest itself, if it's strong enough, it would manifest itself as canting of the net moment at zero field. So now I'm going to present the squid and the anomalous Hall effect data, and we're going to see if we see any kind of signs of non-collinearity. So first, I am showing squid loops in the top panel for 3 different manganese compositions within the ruthenium 0.5 series. And on the bottom, we have the anomalous Hall effect. I'm again reminding that anomalous Hall, the resistance is proportional to the 4C sublattice, and in squid, we have the net moment, which is the sum of the 2 sublattice magnetizations. So let's look at the hysteresis loops that were taken at 300 Kelvin. The magnetization in squid is equal to the net moment. And what we see is that the coercivities between the anomalous Hall and the squid basically match. However, the in-plane part has 2 different components. So one of them is soft and the other one is hard. So in order to understand this better, what is going on, I'm going to zoom into this middle squid loop. And so in ideal world, the hard component would be simply given by this behavior of a straight line. So we would start at the origin where the in-plane moment would be 0. That corresponds to the net moment being fully aligned with in the Z direction. However, as the field is applied in plane, the moment would rotate and saturate fully in plane when we have reached the anisotropy field. So that explains the high field linear behavior. However, what happens at the soft component? So I propose that at 0 field, we have a cone open of the magnetizations. And so upon applying an in-plane field, this cone collapses into one preferred direction that's constraining, that's basically given by the field. So that gives you this little jump, and then later we can see this rotation as we would expect. So what we see, our observation is counting up the net moment, and this corresponds to our hypothesis of non-collinearity of sublattice moments that could arise from competing exchanges, I've explained in the previous slide. I will discuss this in more detail and investigate using XMCD. So now looking at some spin polarization and Hall angle calculations. Both spin polarization and Hall angle show similar trends. Both decrease as a function of ruthenium, which indicates a shift of the Fermi level position upwards in the density of states out of the spin gap. We observe high Hall angles for the x equals 0.5 ruthenium series of up to 2%, which is about 20 times that of what we observe in iron. Then having a look at the longitudinal and anomalous conductivities, what we find is that the longitudinal conductivity across all series is flat and on average has the same value. Then if we look at the anomalous conductivity, we see that in some series, it is independent of the behavior of sigma xx, so the longitudinal, whereas in the last one, we have basically sigma xy being proportional to sigma xx. So they both sort of have the same trend. So in order to understand these graphs, we need to discuss in a little bit more detail what are the two main contributions to anomalous Hall effect. And this is what I'm showing here. So first we have the extrinsic contributions. That includes skew scattering, which is due to spin-orbit interaction, and it scales as sigma xx, which is the longitudinal conductivity. We have another one, which is called side jump, and it's deflection of velocity upon approaching or leaving an impurity, and is also proportional to spin-orbit interaction. And in this case, it is independent of sigma xx. So both those extrinsic contribution, they're expected to increase as ruthenium is increased in manganese, ruthenium, gallium, because ruthenium is the heaviest element, so it should have strong spin-orbit coupling. Then we also have this intrinsic contribution, which is a scattering independent deflection of velocity due to Berry curvature, which depends on the geometrical properties of the energy bands, and it is independent of sigma xx. So now coming back to the results of the anomalous Hall effect and the conductivities, I've summarized here that for different series, we have a different dominant anomalous Hall effect contribution, where for when the anomalous conductivity is independent of sigma xx, we have a dominant intrinsic contribution, and whenever they are basically proportional to each other, we have dominating of skew scattering, which occurs for high ruthenium contents. So now that we believe we have this intrinsic contribution, the Berry phase curvature could originate from either non-collinear spin texture, which I will investigate by XMCD. It could also be due to vial points in the band structure near the Fermi level, which can be found in materials that break both time and space inversion symmetry. And that can be investigated using RPES, but I'm going to focus in this work on the XMCD. So now the aim of the XMCD, as you probably have now gathered, is to investigate the hypothesis of the presence of a non-collinear magnetic structure. And in this section, I will outline the what is X-ray absorption spectroscopy and what is XMCD. I will describe the sample. I will show the results taken at normal incidence, which will include temperature dependence of sublattice moments, as well as showing the spin flop transition near compensation. And I will also look at the XMCD in grazing incidence, which allowed us to construct two-dimensional vector projections of moments. And I will show you the results taken at 10 Kelvin for fields applied both out of plane and in plane. So firstly, X-ray absorption spectrometry measurements were performed with circularly polarized light at the L edge of manganese. Typical excess spectra are shown on the left. The two spectra are subtracted to obtain a dichroism spectrum, which I've now shown on the right. So some rules are basically equations that are used to calculate spin and orbital moments. However, they require the integration of the entire spectrum, which would yield only the net moment. So because I am interested in the sublattice moments, I assume that the areas of the two peaks in the XMCD spectrum shown here, so around the L3 region, so this first peak that corresponds to manganese 4A, and the second peak corresponding here to manganese 4C. So I'm assuming their area is proportional to their spin moments. Now, this is in violation of the sum rules. And what I will get is that the spin moments will be in arbitrary units. And in order to normalize them, I will be using magnetometry data. So I'll be showing you how this can be done. So on this slide is a summary of the magnetic properties of the sample studied, which was manganese 2.2, ruthenium 0.7, gallium, which has a compensation temperature at 123 Kelvin. So from the zero field temperature scan, which was performed in SQUID, I was able to take it and again do the mean field theory fitting to predict what the behavior of the manganese 4A and the 4C sublattices. On the right, I'm showing the SQUID loops of the net moment, and I'm also showing for the 300 Kelvin case, I'm showing the anomalous Hall effect loop, and we can see again coercivities are matching. Then if we take a look at the in-plane component, we see again this quite a strong soft component, which grows even bigger at 200 Kelvin, which it is so big at this stage that you can't really even see the hard component. And of course, at the very bottom, I'm summarizing the exchange energies, where we again have the same hierarchy of exchanges as we've seen before. So now moving on to the XMCD data. First, I wanted to remind you that below compensation temperature, manganese 4C sublattice is the dominant one, whereas above compensation temperature, the manganese 4A sublattice is the dominant one. So we have performed measurements as a function of temperature in a 9 Tesla applied field. So at low temperatures, the 4C moment is positive, whereas at high temperatures, it was the 4A moment. And below, I am showing an illustration of the directions of the sublattice moments and how they rotate in the field as the temperature is changed. So these are already scaled into mu-Bs per manganese. So now I want to show you how I use this data for scaling. So because from MFT, I've calculated the temperature dependence of the 4A and 4C sublattices. Here I'm showing the MFT data with the solid line. And I was able to scale it to the value at high temperatures using the assumption that the 4A moment away from compensation in a 9 Tesla field is fully aligned with the field along the Z-axis. So we're getting the full Z projection of the moment. And for 4C, it was the opposite temperature. So at lower temperatures, I assumed the 4C sublattice is perfectly aligned with the Z-axis. And therefore, we were able to obtain this data. Next, looking at the spin flop near compensation. So here we can see that compensation occurs at around 145 Kelvin in 9 Tesla. So first thing is that when you look at these curves, they don't really probably remind you of the behavior of antiferromagnets. And this is because here we are close to compensation. Net moment is not completely zero. So the residual moment, there is some anisotropy. So we have a much more smoother spin flop transition than what is observed in antiferromagnets. So we've determined the spin flop field to be 7.65 Tesla. And then using the equation shown in the bottom left, I can obtain the anisotropy constant for the net moment. And from the calculations, I find it to be 6.7 by 10 to the 4 joules meters per meter cubed, which is a typical value that we found again and again. Then I've also used the saturation magnetization to find the anisotropy field and used it to find the FMR frequency. And what I find here is that for 145 Kelvin, we have 188 gigahertz. From TR MOG at similar temperatures, our colleagues found 160 gigahertz for similar MRG samples. So we're in the right ballpark. Next, I want to discuss the grazing incidence measurements to construct two-dimensional vector diagrams of sublattice moments. So scans were taken at 2 incidence angles. This, of course, requires rotation of the sample, not the beam in the synchrotron. However, for simplicity, I'm showing the diagrams in the frame of the sample. So also as an example here, I'm showing field being applied in plane. There's also, we were also applying the field out of plane. So the 2 angles of incidence are 90 degrees apart. So one was -70 and the other one was 20. And from the diagram, the measured moment is a linear combination of the perpendicular and parallel components with coefficients found using trigonometry. So those equations of the moment projected onto the k vector are those two linear combinations. And here I'm also showing the corresponding XMCD spectra taken at 10 Kelvin and 4 Tesla field. So then we can take these equations and we can solve for, as simultaneous equations for m perpendicular and m parallel. And hence we can construct a two-dimensional vector. And for out-of-plane field measurements, the calculation is basically the same. So now we want to see what these diagrams look like. So I'm showing you a very basic example. This is data taken at 10 Kelvin with the field applied out of plane along this broken line, the green broken line, and the field was directed as the arrow is pointing. So there's 3 different arrows I'm showing in these diagrams. First is the blue one corresponding to the 4C moment. This one is dominant because we are below compensation. Then we have the red arrow, which corresponds to the 4A moment. And there's the pink arrow, which I had to multiply by a factor of 100. And this corresponds to the spin moment, which is proportional to the sum rule net moment. And so as the field is, so the sample was saturated before the measurement. And then as the field is increased, we would expect the 4C sublattice to basically saturate along the field. And this is exactly what happens. Now, something important to notice here is that indeed, there is a small non-collinearity between the two magnetic sublattices. So this is our direct observation of non-collinearity of sublattice moments. Then now that we know that this method works, we can consider the in-plane measurements with field in plane. So here we've applied a field up to 4 Tesla along this direction. And what we notice is that the sublattices haven't switched, so they haven't saturated along the field. So the first sort of clue is that there is a large anisotropy field. And in order to actually calculate it, I performed a balancing of torques calculation, which I will show in this slide. So we know that at equilibrium, the sum of all the torques must be 0. So there are torques due to the external applied field, and there's also torques due to the anisotropy field. So here I assume the case of uniaxial anisotropy, and hence I can write down the anisotropy energy, which is equal to the anisotropy constant times sine squared of theta minus the intersublattice coupling with the difference of the 2 angles. So in order then to find the torque, I need to differentiate. So I find the negative derivative of the energy with respect to the theta, and that will give me the torques. And then summing all of them. So on the left-hand side, I have the torques due to the external field, and on the left-hand side, and then on the right-hand side, I have the torques due to anisotropy field. That leads to the following equation that will need to be solved. And you can see that I've only got 2 free parameters, which are the anisotropy constant of 4A sublattice and the anisotropy constant for the 4C sublattice. And lastly, but not least, I can find the anisotropy field using the anisotropy constants, multiplying it by 2 and dividing by saturation magnetization. So now summarizing all of the findings. So first of all, we can compare the anisotropy constants of the net moment from spin flop and from this balancing of the torques for the hard axis measurement. We find that the anisotropy constants are very close and they're the same order of magnitude, what we would have expected. Now, the 2 interesting results are the anisotropy constants for the sublattice moments, which turn out to be very large, of order of megajoule per cubic meter. And also the 4C sublattice magnetization anisotropy constant is negative. So what could this possibly mean? So I believe there are 2 possible contributions here. So the first one is that because of the simple uniaxial anisotropy model, we've assumed in this energy equation that the JAA and JCC intersublattice couplings are infinite, which is not the case. Also, this uniaxial anisotropy model does not take into account non-collinearity. So perhaps one explanation for these results would be that this is a manifestation of the non-collinearity, which is not quite captured by our model. However, just a note on the magnitudes, I want to make a comparison with manganese 3 gallium. So here I am showing on the left the cubic Heusler structure, which can be considered in its tetragonal representation, which is marked with the red solid lines. And this then on the right-hand side is the DO22 manganese 3 gallium tetragonal structure with a CO/A of about 1.8. So now MRG, which is also is in its cubic representation, can also be represented tetragonally, which I have marked with these gray broken lines. And here I've isolated it. So now looking at the tetragonal representation of MRG, we get a C/A of about 1.4. So now there's obviously a difference between these compounds in tetragonal distortion. However, the manganeses have similar environments and the crystal structures are also similar. So now looking at the anisotropy constants, we find the anisotropy constant values of both compounds are the same order of magnitude. And this suggests that it is probable that MRG anisotropies are actually large and can contribute to sublattice non-collinearity. To investigate this, the plan is to measure magnon dispersion, which depends on sublattice anisotropy. I have already started working on deriving analytical expressions for the magnon dispersion relations, and hopefully experiments can be conducted soon. Now moving on to concluding my presentation. So first, 2 materials, hafnium and molybdenum, were found to be effective in mitigating manganese diffusion while having small negative effects on the overall device. But it is still probably worthwhile to investigate low manganese-based zero-moment half metals to minimize this issue in the first place. Magnetic domains have been observed in a magnet with negligible stray fields in the Kerr microscope. And MRG has a potential for racetrack memory with maximum racetrack width of about 240 nanometers, according to our results. The properties of MRG, such as compensation temperature, can be varied by changing the composition, and we can therefore suit it for a particular application. The collinear mean field theory model successfully reproduced the magnetic data in terms of the exchange and anisotropy parameters. However, 4C sublattice non-collinearity has also been demonstrated by XMCD, and this non-collinearity can originate from competing exchange on the 4C sublattice. Neutron diffraction experiments just conducted at ILL in Grenoble this month, also on MRG, seem to confirm this non-collinearity. We have observed signal on the 002 purely magnetic reflection, which indicates there is a component of the moment in plane with no applied field. Thank you for your attention.